Today I'm glad to present my work on evolutionary knowledge discovery from RDF Data Graphs, supervised by Andrea Tetamanzi and Catherine Faron. I will start by introducing the general background of my thesis. My thesis focuses on knowledge graph, more specifically on RDF knowledge graphs. RDF is a framework used to represent and link data on the web. An RDF graph is an oriented labeled graph where nodes are linked by properties. As you can see in this example, it can be viewed as a set of connected triples. An RDF triple is composed of a subject, which is an array or a blank node, a predicate, which is an array, and the object of a triple, which is an RDF terms, array, literal, or blank node. The array object of a triple can be the subject of another triple, and this is how triples are connected together, producing an RDF graph. The link open data gathers more than 1,000 interconnected RDF graphs available for humans and artificial agents. RDF graphs are modeled under the open world assumption, stating that a lack of knowledge does not imply falsity. This allows a degree of flexibility in knowledge modeling required on the web. RDFS is the standard to declare classes and properties that are used to build RDF graphs. OWL is an extension of RDFS to represent richer ontologies. It provides additional type of axioms to define properties and classes. Here, I present the declaration of the age property and the person class. The latter is an example of class disjointness axiom between the class person and the class moon. Describing domain knowledge in ontologies provides context to RDF graphs and enables interoperability between systems. Rich ontologies enable the inference of new facts in RDF graphs. Sparkle is the RDF query language to manipulate RDF data in the data store on the web accessible through Sparkle endpoints. The core of a Sparkle query is a graph pattern, that is to say a set of RDF triples whose elements can be variables, and that must match the RDF graph. Here, we want to retrieve the 5 films produced by Tim Burton with the highest number of actors, and we query the DBpedia in the Sparkle endpoint. First, we select the films produced by Tim Burton, and as you can see, film is a variable. Second, we count the number of actors for each film of Tim Burton. We limit to 5 the number of results to be returned, and we sort the result in descending order. By executing the following query, we get 5 results, among which the films Mars Attack or Batman. RDFS and OWL ontologies enable to describe vocabularies, but does not guarantee that RDF data conform to them. In this RDF graph, we will be interested in detecting the bad practice in Benjamin's age information. Shackle is a W3C recommendation to express constraints on RDF graphs in the form of shapes. A shape targets a specific set of nodes in an RDF graph, and it includes one or more constraints to access them. In this example, for each person for which the age is specified, the age value must be an integer. Such a shape enables to detect that Benjamin's age is not compliant with the expected data type. A Shackle validation engine produces a validation report where the error is reported as a violation of the shape. The validation report focuses on shape violations and is non-conform as soon as at least one violation is observed. In the context of my thesis, I tackled the need to enrich RDF graphs with domain knowledge in the form of axioms that describe a specific relation between classes, and shapes that express constraints on the graph. I propose to discover this knowledge from RDF data and in an automatic way, considering incompleteness from knowledge graph, inconsistencies, and scalability issues related to bottom-up approaches, also known as the knowledge acquisition bottleneck issue mentioned by Lehman and Stanley. I proposed an evolutionary algorithm based on grammatical evolution for discovering all axioms and shackle shapes. This algorithm is a particular type of genetic programming technique, and more specifically a population-based stochastic optimization where candidate knowledge pieces are modeled with context-free grammar. In my thesis, I use BNF grammars. A first work has been done in this direction to discover disjointness axioms with promising results. The following 2 lines of research have highlighted challenges in assessing candidate knowledge. Concerning subsumption axioms, I consider an existing possibilistic framework to assess candidate subsumption axioms against RDF data through Sparkle queries. I proposed optimizations of existing queries used to compute exception to an axiom to significantly reduce the computation time and enable scalability in a mining context. Concerning shackle shapes, I proposed an extension of the shackle validation process to consider a physiological proportion of errors in a graph and a probabilistic framework to assess candidate shapes against RDF data. Consequently, I tackled the following 4 research questions. How to overcome computation time issue to assess subsumption axioms under the open world assumption. How to automatically discover class subsumption axioms from RDF data. How to design an RDF graph validation process considering physiological errors in real-life data. And finally, how to automatically discover shackle shapes from RDF data. First, I will tackle the research questions 2 and 4 by presenting my proposed general algorithm to discover new knowledge based on grammatical evolution. This is the grammatical evolution architecture that we implement to model candidate knowledge, axioms, and shapes as individuals through Sparkle grammar, assess them using a fitness function to define their credibility, selecting the best solutions, and selecting individuals to renew a part of the population that has not been selected as elitist to discover new candidate knowledge that we will assess, and so on, until the stop criterion is reached. The goal is to maximize the fitness value of a large set of candidate knowledge, resulting in a set of relevant knowledge to exploit. Individuals are characterized by 2 sets. First, the genotype as a set of codons or integers exploitable by the algorithm, and the phenotype, which is the translation of the genotype exploitable by humans. Here is an example of BNF grammar to represent a very simple, to build a very simple math formula. Let the following genotype of an individual, the genotype-phenotype mapping, we build the genotype form according to each codon to select the corresponding production rule through modulo operator. It produces the phenotype X plus 7. In order to build candidate knowledge that exploit resources from the RDF graph, we extend the previous works to include additional rules in the BNF grammar to inject RDF data as possible values of a rule. In this example, we include the class rule and the value sparkle followed by the sparkle query body. And this kind of rules are automatically passed by the system to perform a sparkle query over the triple store. Finally, we replace the previous rule in the BNF grammar by the sparkle query results. We adapt an algorithm for the recombination phase to preserve the diversity of a population while guaranteeing a wide exploration of the solution space. In this example, we select the two best individuals and save them for the next generation. From the whole population, we select individuals and use them to produce offspring, that is to say, new candidate knowledge. From the selection, we are interested to inject individuals that are not already in the recombination set or in the elitist set, while the recombination size is not reached. This is why I4 is not injected in the recombination set, because it is already represented in the elitist set. From this recombination phase, we produce two new offsprings to assess against the fitness function. Then we will select the best, and so on. We focused on very simple variation operators on the genotype, which occurs with a given probability. The crossover enabled a set of codons to be exchanged between two individuals, and the mutation enables the transformation of one codon by another, sometimes leading to a significant change to the individual. To conclude this section, I proposed an algorithm based on grammatical evolution to discover new knowledge from RDF data. I propose an extended BNF grammar that exploit RDF data as production rules, and a recombination algorithm to preserve the diversity of the population while guaranteeing a wide exploration of the solution space. This contribution opens up the discovery of our axioms and shackle shapes. I will tackle the subsumption axiom discovery, but first I will present my contribution regarding the optimization of the computation of exception to candidate subsumption axioms, which tackle the research question how to overcome computation time issue to assess subsumption axioms under the open world assumption. Class subsumption axioms implies two class expressions, let sub the subclass and super the superclass. The axioms expresses that all instances of sub are instances of super. For instance, all cats are animals. And we consider the whole functional syntax to produce candidate axioms with a BNF grammar. Subsumption axioms assessment is based on existing work and makes it possible to take into account ignorance in RDF data. Among the instances concerned by an axiom, we distinguish the confirmations. Some are exceptions, but it is possible that some are neither one nor the other. Consequently, we compute the possibility of a subsumption axiom based on the number of exceptions. And if it's fully possible, that is to say 0 exceptions, we can compute the necessity of an axiom based on the number of confirmations. We use these metrics to define the acceptance rejection index, ARI, measure of an axiom based on the possibility and necessity measure for the automatic assessment of the axiom. I propose a new Sparkle query to compute the exceptions of an axiom in order to avoid redundant computation. As we can see in the schema of the original query, some types were redundant, such as T1 and T2, and the same individuals was computed many times. To give you an idea of the impact this can have on the computation time, are the classes that are best represented in DBpedia 3.9. These are the classes whose instances may return several times in the computation, with drastic consequences on performance. First, I proposed a multi-threading system to assess several axioms in parallel, which reduces the overall time needed to assess axioms. Second, I implement Sparkle queries in 2 steps. First, I filter redundant types, and 2, I compute exceptions from types found before. Chunking techniques have been implemented to further speed up the computation. Finally, I propose the different Sparkle query to filter redundant types through Sparkle federated query and the loop operator implemented in the core semantic web factory. To analyze the effectiveness of these optimizations, I compared the result of the SOTA method on a set of axioms evaluated against the DBpedia 3.9 dataset. I analyzed the equivalence of the result in terms of acceptance rejection index values, which must be the same, and the difference in CPU computation time. In the same way, I analyzed the CPU computation time saved with the usage of the loop operator. First, I observed that all array values are equivalent between the SOTA technique and my method. Second, I observed that 82% of axioms are faster to assess with my proposed Sparkle queries, with more than 600 minutes CPU time saved in average, compared with the original method. I also reduced the maximum computation time observed by more than 70,000 minutes. Interestingly, we saved the CPU times for 95% of axioms with Sparkle's federated query that use the loop operator. But the average time saved is less impressive than the previous one, with only 12 minutes saved. To conclude this section, I proposed optimizations on the class subsumption axioms assessment have significantly reduced the computation time. Only very few axioms are slower to assess, and the extra time is minimal compared with the benefits. And this optimization in assessing candidate subsumption axioms opens up the possibility of evolutionary discovery of subsumption axioms from large RDF graphs. In this section, I will now present my contribution on the discovery of subsumption axioms between complex class expressions. I extend the discovery of subsumption axiom between atomic classes to the discovery of subsumption axioms between complex class expressions. I considered 3 types of class expression. The intersection between 2 classes. In this example, we consider instances that are humorist and actor. Object some values from expression. In this example, we present the class of all the individuals whose at least one platform value is a software instance, and object all values from expression. In the example, we present the class of all individuals whose all platform values are software instances. Here is a BNF grammar used to build candidate knowledge subsumption axioms with complex class expression, with some values from expression, all values from expression, intersection of 2 classes expression, or atomic class. In order to assess the efficiency of this approach, we considered the discovery of axioms from the DBpedia RDF dataset. This is a very challenging task, as it contains more than 100 million of RDF triples. We chose quite modest parameters in the sense that they they do not demand many resources, but with a large number of executions to stimulate exploration of the research space. And we used the SOTA fitness function, which considered the supports, the possibility and necessity values of an action. Despite modest grammatical evolution parameters and the problem's difficulty, we observed that some of the discovered axioms have a positive RIV score, and 25 of them have at least one confirmation. The most credible results were obtained with the smallest population size. Some examples are interesting to analyze. The first one, baronets are persons, has been discovered and can reasonably be considered true. The second one, reptiles are species, appears inaccurate since the species class is too general. This is why it lacks confirmations. The last one suggests that all individuals whose at least one platform value is a software R works is not meaningless, but we cannot decide for a large part of instances concerned by this axiom. And we observed a few number of confirmations and 6 exceptions. This is why the ARI value is negative. Finally, we observed that the CPU time related to the axioms assessment is correlated to the number of exceptions. Globally, the optimizations enable to maintain a very reasonable computation time for the candidate axioms assessment. To conclude on this contribution, we propose the BNF grammar to build subsumption axioms that can be composed of complex class expression. Experiments show that the proposed approach enables the discovery of class subsumption axioms expressing certain domain knowledge over a large RDF dataset. And this concludes the presentation of my contributions on the discovery of all axioms. Now, I will tackle the discovery of shackle shapes, starting with a presentation of the probabilistic framework I propose to validate RDF graphs against shackle shapes. As mentioned above, the standard shackle validation is used to report violations of constraints by the nodes of an RDF graph. The graph is not compliant as soon as one violation is observed. This strict validation limits an automatic discovery of shackle shapes. This is why we proposed a probabilistic framework to consider a physiological proportion of error from RDF data during the shackle validation. By physiological errors, we mean that errors in RDF graph are unavoidable or inherent from RDF data. For instance, they are the result of collaborative building of large RDF graphs, like Wikidata, or automatically construct RDF graphs like DBpedia. Considering a shape and an RDF graph, we define the reference cardinality as a set of tested triples during the shackle validation. We have chosen to consider the tested triples instead of the nodes because a single node can involve many violations against a shape if this one involves many constraints. Among the tested triples, we distinguish the set of triples that violating the shape and the set of triples respecting the shape. We assume that the validation process of a shape follows a binomial distribution, considering a theoretical error rate. From this assumption, we define the likelihood of observing the number of violations, and it's given by the disadaptation of the binomial mass function. We also define a generality measure expressing the representativeness of a shape considering the RDF graph. It is a proportion of triples in a graph that are tested with the given shape. We have enriched the standard shackle validation report with these metrics. We define a small vocabulary with an space denoted by the prefix PSH, like probabilistic shackle. This vocabulary is indexed by linked open vocabularies, and the documentation is available on the web. Based on this probabilistic framework, we have designed an acceptance criterion for shackle validation based on hypothesis testing. In this example, we have the likelihood distribution according to the number of violations, for which the max value is given by the theoretical number of violations. An RDF graph is valid against a shape if the observed number of violations is lower than the theoretical number of violations without any hypothesis test. Otherwise, we perform an hypothesis test, more specifically the testing for goodness of fit, and validate RDF data graph if the difference between the theoretical and the observed number of violations is not significant. In this example, the RDF graph is valid against the shape because we cannot reject the null hypothesis. In order to assess the potential of this approach, we have experimented with the evaluation of a subgraph of the COVID on the web knowledge graph against a set of shapes. COVID on the web RDF subgraph is composed of scientific articles annotated with name entities, and the characteristics of the dataset is presented below. These shapes represent association rules found in previous work, using a slightly different version of the RDF graph. The idea is to empirically estimate the theoretical error proportion of the RDF graph by evaluating this graph against this set of shapes with multiple rates of physiological errors. The association rules used have been transformed into shackle shapes, whose format is the following. We'll target all the scientific articles of type the name entity, that is the antecedent of the association rule, and we translate the constraint that the scientific articles must also be of type the name entity, that is the consequent of the association rule. The first results show that our approach is able to highlight a physiological error proportion that maximizes the average likelihood measure obtained during the evaluation of RDF data against the shapes. It suggests that the realistic physiological error proportion is 50%, with an average value of the likelihood measure equal to 0.03%. This figure represents the proportion of shapes that are respected or not respected by RDF data, with or without hypothesis testing. Focusing on the result given by a theoretical error rate to 50%, we observe that 65% of shapes required hypothesis test, and 74% are not respected. But this proportion of validated of RDF data that validate shapes after hypothesis testing represent 33% of the whole, and this is a non-negligible proportion. To conclude this section, I proposed a probabilistic framework to validate RDF data against shackle shapes, with the additional metrics of likelihood and generality, and an automatic acceptance model based on it. Experiments have shown the potential of this approach to estimate the theoretical error proportion from the evaluation of RDF data against a comprehensive set of shackle shapes. This opens the shape discovery from RDF graphs using this framework. In this section, I will present my contribution on the discovery of shackle shapes from RDF data. I propose an approach similar to the one for the discovery of all subclass of axioms. That is to say, testing candidate shackle shapes using the probabilistic framework I just presented for shackle validation. In order to assess these individuals, we first define an acceptability measure based on the probabilistic framework. This measure is equal to 1 if the shape is accepted by the probabilistic validation. Otherwise, we use the likelihood value, which is normalized by the maximum value of the likelihood distribution, in order to give a reasonable score for individuals that are very close to be acceptable. Finally, we use this measure to define the fitness function and use the number of confirmations as the support of a candidate shape. Here is the BNF grammar used to produce candidate shapes representing association rows. Consequently, it produces the same shape structure as presented before, with a target class on antecedent and as value constraints on consequent. For experiments, we are interested in the discovery of shackle shapes using the BNF grammar presented before from the RDF subgraph of COVID on the web used for probabilistic framework experiments. We focused on the impact of the ratio population size effort to invest and on the selection pressure and analyze their impacts on the shapes discovery. Here are the general conclusion of this experiment. The results show that a significant effort with a small population, that is to say a high number of generations, provides the best results regarding to the average fitness score, average likelihood, average computation time, and so on. Concerning the selection pressure, we observe two trends. A low selection pressure results in fairly homogeneous individuals for the above indicators, whereas a high selection pressure results in better elitist individuals and more variable individuals for the others, highlighting a wide exploration of the solution space. Finally, we observe the linear increase of the CPU time according to the number of violations. This gives us the intuition that the approach is scalable. To conclude this contribution, we proposed an effective approach based on grammatical evolution and a fitness function based on a probabilistic framework for discovering constraints over an RDF graph. We proposed the BNF grammar to build well-formed shapes that express as value constraints and a relevant fitness function based on the probabilistic framework that enable the discovery of a large set of credible shapes, taking into account the inherent error and incompleteness from RDF data. In this section, I will now briefly present the web application I developed to monitor the discovery process. This is RDF Miner. All the contributions have been implemented and tested in RDF Miner, a web application for discovering new knowledge from RDF data. I proposed an interactive interface to control the discovery process, settings, and so on, and a dashboard to consult and analyze results both in real time. Additionally, we can download results file to exploit the discovered or axioms or shackle shapes. To conclude this presentation, here is the wrap-up of my contributions. I proposed an evolutionary algorithm based on grammatical evolution for discovering all axioms and shackle shapes. The approach enables to generate candidate knowledge based on BNF grammar to fairly assess it using RDF data, and finally enrich ontologies or validating schemas to improve RDF data quality. Moreover, I proposed Sparkle queries optimizations in the case of subsumption axioms, which significantly reduced the computation time for axioms assessment, and a framework to exploit probabilistic informations in shackle validation reports, which enables RDF data validation with hypothesis testing. I developed a web application to exploit the grammatical evolution algorithm and discover new subsumption axioms and shackle shapes from RDF data. The code is open source on the web. There are many perspectives arising from this work, and I've highlighted those that seem to me most important. On the evolutionary discovery, the novelty search technique seems relevant to improve searches in the solution space by rewarding individuals that are different from the others. Grammatical evolution techniques, such as structured grammatical evolution, are also interesting in this context, more specifically to address the low locality issue mentioned in the literature. Of course, it will be useful to explore automatic discovery of other OWL axioms and other heuristics to evaluate them. For example, work exists to predict the score of subsumption axioms, and it would be interesting to test this method in a mining context. With regard to shackle shapes, it would be interesting to analyze other types of constraints to be discovered from RDF data. Similarly, we might wonder if a heuristic based on possibility theory is applicable, and if so, compare the results with the probabilistic framework. Here is a recap of my contributions on both semantic web and evolutionary algorithm community. Thank you for your attention. If you have any questions, please let me know.
Thank you very much, Rémi. So, Rémi, you defended a PhD on evolutionary knowledge discovery from RDF Data Graphs. That's no news, right? On today, and you did so respecting the perfect timing, and you covered all aspects of your work, which can be positioned at the intersection of semantic web, data mining, and evolutionary algorithms. You did so in front of a jury who are experts in data science, knowledge representation, evolutionary systems, and you managed in your talk to introduce your domain and convey the technical results in a very clear presentation, providing motivated and exemplified methods for each one of your contributions. The presentation successfully conveyed the relevance and efficiency of evolutionary approaches for discovering various types of knowledge, and their robustness in the case of incomplete or erroneous data. You were able to show how you formally defined and rigorously validated your methods, detailing your methodology and the resources you used for the evaluations. In your talk, you were able also to structure in technical section your different contribution and addressing your different questions, namely optimize methods to assess candidate subsumption axioms and open world assumption, automatic discovery of class subsumption axioms from RDF datasets, RDF data validation in real datasets containing error, and automatic discovery of shackle shapes. The jury stressed that the thesis addresses an important and timely topic in the broad field of artificial intelligence, combining evolutionary computation and knowledge graphs to discover new knowledge, and that this was published in international venues of the combined domain, with some of your publication being awarded. The jury found that you pedagogically presented a significant and original contribution to automatic knowledge acquisition from RDF data. In its comment, the jury also appreciated the fact that the results were validated with open source implementation and real-world dataset, that you made openly available, which allows reproducibility. Very good. The question of the jury covered all the domain of the contribution, considering very different technical aspects. For instance, the extension of the expressiveness of the main axiom, the characterization of incompleteness, the implications of considering dynamic data, and so on. There is a whole list of the questions I will not repeat. And you managed to answer this technical question on your work demonstrating your expertise, and you also showed that there were many perspectives to your work. As a result of your excellent work, the jury unanimously decided to award you the PhD from Université Côte d'Azur. Congratulations. You want the mic?
Merci. En présence de mes pairs, parvenus à l'issue de mon doctorat en informatique et ayant ainsi pratiqué dans ma quête du savoir l'exercice d'une recherche scientifique exigeante, en cultivant la rigueur intellectuelle, la réflexivité éthique et dans le respect des principes de l'intégrité scientifique, je m'engage, pour ce qui dépendra de moi, dans la suite de ma carrière professionnelle, quel qu'en soit le secteur ou le domaine d'activité, à maintenir une conduite intègre dans mon rapport au savoir, mes méthodes et mes résultats.
Congratulations.
Comme le buffet est presque prêt, je vais essayer de ne pas être trop long. En premier lieu, oui, évidemment, un immense merci à mes superviseurs, Andrea et Catherine, pour premièrement m'avoir fait confiance pour réaliser cette thèse. Et durant ces 3 années, j'ai énormément appris à vos côtés. Ça a été un immense honneur de pouvoir travailler avec vous. Et de pouvoir peut-être continuer aussi à travailler pour de futurs projets. Je tiens à remercier les membres du jury pour avoir pris de leur temps pour relire, évaluer mes travaux et pour leurs questions pertinentes. Un grand merci à vous. Aux membres de l'équipe Wimix, un immense merci pour... j'ai énormément appris à vos côtés. On a partagé de bons moments, notamment pendant les pauses café, qui sont nombreuses. Et bien sûr, à mes amis, un immense merci pour votre soutien. Et ensuite à ma famille, à mon parrain qui m'a fait la surprise de sa présence, à ma petite sœur que j'embrasse et à mes parents qui m'ont tout donné et m'ont permis d'en être là aujourd'hui. Et voilà, un grand merci à vous tous pour votre présence. Ça me fait super plaisir de vous voir à mes côtés aujourd'hui.